Trustee Weber, this is an exciting day.
Yeah.
I first want to really thank everybody for taking an interest in our Door County icons. It's important that everybody in the county take part in saving all of our most unique places, because if we tear them down, there's no reason for anybody to come and visit us. And we all rely on tourist incomes in one way or another throughout the county. What one city does, another city suffers, so we have to be involved countywide. Secondly, I want to acknowledge our Sturgeon Bay Historical Society members, and if you could put your hands up so that we can all thank them for all their hard work. And especially to our donors, that some are anonymous and others are like Bill Parsons, who's always there, and Betty at every turn to help out in the community. The studies aren't cheap. We're in debt now, so if anybody wants to help. Not too bad though, and it's gonna pay off big time. So I guess that's it. We can open the floor for Dan, Dr. Dan Tingley.
Well, thanks for coming tonight. I like to be at these presentations. I was just telling a little personal story before, because I've been in these situations many times. And I can remember a time in a place called Wagga Wagga in New South Wales. I had been asked to come in and teach a course and then inspect a 3-span bridge. It was 100 feet a span. It was built in 1892. And they had wanted to save the bridge. And so I was asked to come in and present to the public after I'd completed my findings. I knew I was in trouble when they picked me up in a police car to come into this session. And it was really a hotly contested issue. 4 councillors for it, 4 councillors against it, and the mayor sat on the dividing line. And my job was to present to 500 people who had a vested interest in seeing it go and stay, if you know what I mean. And so it was a really kind of rocky time. I was expecting rotten tomatoes at any time. And, out of that time, it hardened my resolve. Those times give us character. That's the simple of it. And it doesn't matter whether you're a Democrat or a Republican. It doesn't matter what side of the fence you're on. When you lose track of your past, you lose track of your future. And that's the story for us. And just because things get old and gray doesn't mean they're no good, or I'd be done. And so at the end of the day, that's what drives me. And so I've got a little presentation to make today to you all about this fabulous tower. I had a chance to go out today. They picked me up at the airport and I went out. My technicians had been there before. And it's just spring is blossoming and beautiful out there. Man, it was beautiful. I wanted to tear the plywood down on that and go to the top so bad. I didn't do it, but anyway. So without any further ado, I'm going to start and continue. And hopefully you'll all be able to see a little bit of a teaching session. So I've got this board because sometimes my hands and feet can't move fast enough and I actually have to draw. So I'm going to take you through a little bit of a roller coaster ride. And my talk is kind of like this. It starts off with a little bit of background about timber and wood and why wood doesn't have a use-by date. Use-by date. We're all used to seeing shelf life on things. When we buy glue, it's got shelf life. When we get cars, we know they wear out at so long, right? And so we think of timber wearing out, but wood doesn't have a use-by date. And so we're going to talk about that. And then we're going to go into some of the aspects of other towers that I've been doing around the world. Right now, I'm just finished a design on the tallest tower in the southern hemisphere made with wood, with no guide wires. It's 100 feet taller than this one. And it's got 3 legs, not 4. And it was built many, many years ago with round logs, not squared ones. And so they charged me with the job of inspecting it and developing a restoration for the saving of it. And then I'm going to talk about another tower, about the height of this one that we did save and how we did it. So that's kind of a thumbnail sketch of what this is like. And away we go. And I've got room at the end for questions and answers, you know. And you might have enough of me by the time I get 3/4 of the way through it. So if you do, go like this and I'll just quit because I am rather sickening. If you're steel and concrete minded, you probably get sick of me halfway through, right? I'm sold out to timber. I make no excuses for it. None. I'm just sold out to it. At 65, there's no turning back for me. This is the way I am. So off we go. This beautiful tower and the plywood. There's two factors about this. There's this beautiful plywood tower, and then there's this plywood. And so our job, my job, is to inspect it, find the bad actors, and understand how we take the plywood down. That's as simple as that right there. And so, as I said earlier, when the reporters were asking me, you know, how much of this tower is still good? 80 to 90%. If any of you had a car that had 80 to 90% good, a house that had 80, 90% good, if you had anything in your house was 89, would you throw it out? No. No. So why is it? Well, with structural things, it kind of makes a big difference because we have kind of a weakest link theory. If we're going to hang from the steel bridge that you guys managed to save out here, and someone brought up a chain to you, and they had this big chain, and they said, we'd like you to hang from the bottom of that bridge. And you say, well, do you know how strong is that chain? You said, well, the average strength is 21,000 PSI, the average. Would you be interested in the average or the weakest? No, you'd want to know the weakest link, wouldn't you? Because if one was good for 50 pounds, most of us wouldn't make it if we were hanging from it. And so that's what it's like with a tower. We look for the weakest link, don't we? Because if we can get the weakest link and find them, we can fix them, and then we save it. And that's what it's about. So that's what this talk is about. And so we were commissioned by the association, the foundation, to come in and take a look at this tower and use advanced technologies to understand it. And then our second phase was to develop a design solution to restore it. And then with that, a level C estimate, which is plus or minus 15%. And I'm going to save that punchline for the end. And so who am I? I work for Wood Research and Development. I'm their senior structural engineer, timber structures engineer, and wood technologist. I have my master's in structural, and then I have my PhD in wood technology and structural out of Oregon State. If you've been to Oregon, you know it's the land of the tall trees. Things are based on wood out there. And so that's where I went. And you can tell by my funky accent, I'm Canadian. I'll try to put the right emphasis on the wrong syllable for you, but that's just how it is. I've been in America for a long time, and my kids, you know, they say to me, they're all dual, and they say, Dad, why didn't you become American? I said, well, it's not because I don't like Americans. I said, if it goes to hell in a hay wagon here, I can go home. And so there's those of you who are going to agree with that and disagree. Now, I said, stay away from politics. So anyway, having said that, you know, I'm pleased to be in America, and I consider myself American because I love this country. And I've learned to love it in a way that I didn't have an appreciation for 35 years ago. The freedoms in America, the ability to be on the cutting edge around the world. And so many countries look down their nose at us, but we are free because we are at that cutting edge all the time. That's a great thing about our country. It's a really good thing. Never lose track of that. So anyway, who am I and who do I work for? I've said it. And this Wood Research and Development, who are we? We're a code-certified test agency. That's International Accreditation Services, certified as a third party and as a test lab. So people will come to us and they use us as a coat hanger. What's that mean? Structural engineering firms around the world seek us out when they've got an old building that they have to repurpose. And they have to understand what the old timbers in that building are capable of doing. And we come in and test them and tell them what design values to use for those timbers. We are a coat hanger. That's what they call us. So then they can put the liability on us. And we pay a lot for our errors and omissions. Just a little bit of bragging, not to brag anymore, but I'll do it just one time because it's an expression of bonification. Our group was nominated for the Civil Engineering Research Foundation for our work in high-strength fiber and wood back in '96. This is for the G21. We reached 100 finalists, and then we won that award. And then the next year we were nominated for the NOVA Award, which is all construction materials. We won that one. It's the only group to ever have won both of them, back to back. And guess what? It was with wood. No, I didn't say steel or concrete. I said wood. And so that's another great thing. So that's the last of it. I have a few patents in this area. Most of them are off now, 42 to be exact, in many different countries. So some of my best patents happened by accident. You just dropped a block of wood on the floor, the butter side went down, picked up fibers in it, thus come fibers in a glue line. And if you're out buying glue today, anywhere at Home Depot or the rest of it, you're going to buy glues that were based on my patent. And it happened by accident. I had nothing to do with it. Just dropped it. And recognized 6 months later it had 50% more shear. And I'm willing to admit it. So anyway, this has developed a passion in me for engineering over the years and saving stuff, and been around the world doing it in different places, helping people save their timber. And the Discovery Channel came in and have asked me to do how stuff works with wood. And we filmed that at our lab. If you've ever watched that series, How Stuff Works, the wood end of it is ours. So we do quite a bit of this work, and we teach. We teach courses, 16 in total, level 1, 2, and 3 in timber and design, inspection, maintenance, and restoration. One of the few groups that teach these courses. And we teach them all over the world, as you can see here. So I'm no stranger to being in front of a group like this and teaching courses such as timber design. And we test things in these courses, and we break them, and the students have to fix them with high-strength fiber and restore them to 150% of capacity. So when I can teach a student how to take a broken beam and restore it to 150% of its original break capacity, I welcome the challenge of a bad actor in a tower in Wisconsin. Right there. So that's the story there, and you can see me teaching and the guys all teaching themselves as I move through these slides because I've got a lot to go. And we teach them how to wrap things. We're going to wrap a pile like this or a utility pole, People don't understand the basic difference even, engineers lots of times today, because they don't take any courses with timber anymore. Engineers graduate, they might have half a term a course on timber. Lots of them don't even have timber. And young engineers grow up and they come out and they get into steel and concrete because that's what they know, not timber. And when I ask for hands up in a group of engineers and ask them to tell me the difference between a utility pole and a pile, rarely do I get an answer. A utility pole goes in the ground butt first. A pile drives tip first. That's a pretty big difference because this tower is what? It's got columns that are on the concrete butt first. And so interesting little differences that are pretty important when you're going to assess the capacity of a structure. As you hear them being taught how to wrap them with high-strength fiber in a way that allows you to restore capacity. And then do things like this to the finished column. Wrap it with fiber, restore its capacity, and then put a diffuser in it. Well, what's a diffuser? It's a naturally occurring basalt. And a friend of mine, who's now in the Caribbean, retired a long time ago, used to watch John Wayne movies. He's a John Wayne movie buff. And in these movies, you always started off by seeing a wagon wheel and a cow skull. And he thought to himself one day, why don't I see the wagon? Because the wheel's in the mud and the water and the sand. Why is it that the wagon's not there and the wheel is? And so he started to investigate and found out that the wagon wheels that went in the silica across this country hundreds of years ago had basalt salt leach up into the rim, and the salt neutralized the acidic pH wave of the fungi, the fungal colony, and preserved the wood. And he said, if I can learn how to flow that, and he did, I think I could make some money, and he has. And he learned how to put those together. And an anhydrous salt, it's a dewatered salt, that only starts to distribute in the wood when the wood reaches the point at which wood decays, 22%. And it sits in there like a mothball, unused, until it's needed. Now, 10 years even ago, we wouldn't have this technology. We wouldn't have the high-strength fiber 20 years ago. And so much of what we have today to fix old timber buildings and timber structures comes from new technologies that have been birthed. And so from these courses, we train students in how to do things correctly, and then we give them certificates and continuing education units, and you can see here training all the railway people in Queensland Rail in Australia, and all the inspectors in New Brunswick, Eastern Canada. And so all over the world we go, up almost at 1,000 now through that level 1 course around the world. So how do we do things? We test things to establish codes. And at our lab we have great big beam testers where we can put beams, full-scale beams into the testing rig and bring them to failure and understand their capacities and put strain gauges on them to measure strain and understand the wood more intricately, such that when we get an old log, an old girder from an old railway trestle that's 100 years old, we can learn how to fix that old girder in situ and keep the trains going. Or we have fire resistance rating testings where we have assemblies where we can put a cover on them and then bring them up to 1500 degrees C in 5 minutes and watch them burn and fail and understand the fire resistance rating of the structures. Another one of the things we do, as you can see here. And wood is really good in fire because it chars and shuts down further propagation. It doesn't expand and blow out joints. And so then we learned how to build high-strength fibers with Kevlar and carbon and make these long strips of high-strength fiber that are 5 times the strength of steel at 1/5 the dead weight. And here you are here with 2 miles of fiber on one roll. And you unroll it like a Band-Aid and cut it at strategic lengths and put it where you want to in the structure and restore it in situ. Keep it going. And all kinds of things fell out of that, to ways to restore existing structures, because we could take the fiber and replace 42% of the wood, or take a degraded piece of wood and increase its capacity 3 times, and thus restore things in situ. So we evolved into lots of restoration, testing pieces to understand that restoration, putting high-strength fiber on it, including round logs like we have in the tower. And there's my girl. I was at the lab one night, and that's my girl, Beth. I love her dearly. And I look around, and then she's up underneath this log, and she said, "Look, Daddy, I'm Mr. Atlas. I'm holding the world up." And before you accuse me of child abuse, you'll notice that the load head is not on the log, okay? And it's completely secure, so she's okay playing there. She would be embarrassed to tears now if I heard told this story, because she's up in her teens. So, you know, it's our kids that keep us going. So you can see here wrapping these piles and so on to understand their capacities, and lots of this testing using strain gauges that help us understand when you put a piece of reinforcement on a column or a pile, how is it going to respond? And then developing a way to do it so that it kind of fits in with the aesthetics. You can see the imitation wood grain we had on that one to increase its capacity and have it look good. We use finite element analysis to know that when you wrap a pile, you can't tight wrap it, because when you wrap it, capillary action brings the water up in it, expands the pile, it puts hoop stress on the reinforcement and fails it. It separates and fails. And you can see the stress down there at that red point, 29,000. When you put just a little tiny gap, 0.61, about 1/16 of an inch, you can get it down to 11,000. So understanding these things are important for us as we test these piles to deal with them. In this particular test, I had students that had an old fence post made of Douglas fir. It was 8 inches in diameter. It was decayed, laying on the ground out back of the lab. And they were keeners, and they came to me and said, "Dr. Tingley, could we have the materials necessary to try to restore this old fence post? We'd like to test it after we restore it and see what its capacity could be brought up to." I said, "Well, okay." Being the teacher that I am, little did I know they'd put $5,000 of reinforcement in this post. But anyway, you know, it was a good exercise. And so they restored it, and they said, "Well, let's go test it." It was capable of 1,800 pounds when it was new. Well, I had a load cell in my test rig at the time, a 100,000-pound load cell, and I had to stop it at 99,000 pounds because I didn't want to ruin the load cell. It finally failed the next course at 146,000 pounds. And it was rated for 1,800. Do you suppose we can fix the tower?
I think so. I'm not sure yet.
So anyway, that's it there. Restored to be back in service and keep it going. We're doing lots of different things around the world. I thought you'd be interested in this. This is a dam that I'm fixing up in Saskatchewan right now. We just went in, inspected, designed a solution. And on the spillway, you can see this woman dressed here by the spillway. I'd use this, but it doesn't work on this. But you can see her here. And this spillway was built in 1888. You ready for that one now? That's 1888. The Alaskan yellow cedar that's used here in the spillway is still there today. The planks that are there today were installed in 1888. And it resonated with the city when I said, let's save them. Because everybody else said, let's bulldoze them out. And so my idea is to fix them. And here they are here. You're going to use that same, and they're covered in water all the time. But the reason they didn't decay is because what? They're waterlogged. And there wasn't enough oxygen. And so they didn't decay. And so that keeps them going. And so look down in here where it would decay because there's enough oxygen, moisture, and temperature. And we're just going to go in there and fix it. And this is a design solution we have right here, restoring it with all in-kind materials and putting it back into service. And the council is really excited about it because it's a heritage restoration, which resonates with the community. This is an interesting one. You guys are boat builders around here. I don't know if you ever knew that in Canada we have this boat called the Blue Nose. If you've ever been across the border and you got one of our dimes, it has a sailing ship on it. It's called the Blue Nose. And this is the building it was built in. And we've got to restore it right now. We're in the middle of restoring it. It's amazing. Don't you love it? I mean, come on. Really, look at these old arches. Look at them. I mean, it's amazing what they did back then. The funky part of it is depending on what boat went through last, even the tension collar ties in some of them are missing. Like, how is that building standing up? They're gone. So, it's an exciting thing for me to look at restoring this building and bringing it back to service. This is a head wall for a gold mine built by Teddy Roosevelt back in the turn of the century in Western Australia. He went over there and took an assignment and built this head wall in a gold mine with Douglas fir out of Oregon. And they want to restore that piece by piece. See, there's great stories of restoration out there today. This is a cotton mill at Old Miss, 20,000 square foot of floor. We actually were able to help them understand where the timbers had, not only what kind they were, but where they were cut down so that they could create a kiosk with a life tree so they knew where the timbers had actually come from. Is that exciting or what? Come on, are you with me in this program? Jeez. I mean, really, right? I mean, this is what we want to see happen. And here are the old timbers, the poor buggers, have been painted. You never paint a big dimension timber. If it's over a minimum dimension of 2 inches, don't paint it. If you paint it with more than 29% solids, you lock in the moisture and it decays from within. Stain it. Don't paint it. It's one of the top 10 things we do wrong today with heavy dimension timber. And they did it. And it leaked from the outside, water got into the middle, paint held the moisture in, and it decayed from the inside out. And so we had to restore this old building. This one you know right off in Racine. Yes, I did that job. See, you probably knew about me back then. No. Anyway, 26 years ago, Bentley and Son came to me and said, Johnson Wax Foundation needs to fix this Frank Lloyd Wright building. He's a great architect, not much of an engineer, but a great architect. Anyway, they said, we want you to fix this building because the spars in there, wing spread it's called, the spars that are on the big chimney in the center, these spars, there's been leaking roofs, which was a hallmark of a lot of his buildings, and they decayed inside. And they said, we want you to fix it, but you can't take a single piece of trim off the inside. You can't take crown molding off, you can't take baseboard off, everything on the inside has to stay the way it is. And so we built a building over the building and peeled it back from the outside and replaced the spars with carbon reinforced wood in this building. It was a really fabulous job for me. I loved it. As you can see here, the inside and the outside. Who's been there? Yes, right.
I have to tell everybody, about 40 years ago, Palmer Johnson crew from Sturgeon Bay went to Wing Spread and replaced the roof.
No way. That's amazing.
All right.
Right? Can you imagine we circled the wagons and now we're meeting, right? What do you say about that? What? I won't blame the rakes on you. Okay. So you can see this great big thing here, look. And we had to build a model and just restored it, and here's the inside now restored, of course. And I thought you'd all like it. Right down to totem poles. We do it all. Because totem poles, they often put heavy solids paint on them. And where they'll go is right at the bottom where they paint them, where the moisture's enough up from the ground. And where they go at the bottom, they get to leaning. And then they become a life and limb hazard. Fall over and get somebody. So, you know, to this one, where's this? Oshkosh, Fond du Lac. They liked it so much they built 6 of them. And that's my design. It's a girder under Tudor arch, you know, light ped, vehicular bridge. So I do lots of this stuff, and I've had a lot of great routes in Wisconsin over the years. So look, we also develop manuals on restoration techniques for steel, concrete, and wood. I'm on Committee 10 for railway, bridge management safety, and I head up a new committee producing a new handbook of conventional maintenance practices for bridges of all kinds. And we'll be publishing this in June, be the first of its kind. And I just finished a wood guide to construction systems. Bragg Nolan and I produced it. It's a new text being used by universities to teach students on mass timber. Oregon just passed the 20-story law. We're now going to have 20-story timber buildings. The next coming up is in Saudi Arabia. They're now going to, by 2026, have a 126-story timber building. Mass timber is the single largest growth market in the world today. Lend-Lease estimates that by 2026, 30% of downtown cores will be built with timber. Why are we taking towers out that are timber? Even de Blasio in New York said they're putting a moratorium on steel buildings. They're not carbon friendly, and timber is. You'll be sick of me when you get done, I'll tell you these facts. Senseless trivia. So we developed this way of being able to tell what goes on. Roy Pellerin and I in the 80s had the USS Constitution was docked in Boston, and the Navy had its only timber sailing ship, and they wanted to know if the spars were bad and something was bad. And so we adapted this continuous lumber tester device so that we could pick up a compression signal, and we could take this hammer and stop, and we could take this old piece of timber, which comes from the granary. I got it today. I didn't take it through security. And you can see we can basically hit this piece, and it sends a compression wave through the piece. And it measures first time of flight. It measures it to the millionth of a second. Now, the last thing you want to do is pack that in your luggage. We have to all the time because TSA just hates timers on planes. And so this thing gets roughed up pretty bad. I'm sure they figure it's a football. As you can see, they're all bent out of shape because when they get them out of my bag, they say, well, I wonder how far this will go. And bang-o, because it's a really kind of fine-tuned instrument, and you don't want to be kicking it around. It's measuring to a millionth of a second, so it doesn't like to fall. But anyway, that's what we do, and we developed it back then, and it helps us determine lousy wood. And so what Joe's doing here, this guy is the guy that was one of the technicians that inspected your tower. And so he's in Montezuma, Georgia, underneath an active railway line, using this stress wave timer to measure the spike damage down through the girder so he knows how to fix them instead of taking them out, because they have a train every 48 minutes. They're not going to take those out. Can't get them out in time. So they want to know how to fix them in situ and diffuse them and keep the trains going. And that's why these technologies are so important today for us in our economy, to keep things going. And so here he is. He's got the turfer line underneath the track. You can see this guy here he's clipped to. He's quite a ways up in the air. This goes underneath the track. The trains are going. He's figuring out how bad the girders are and where, and then he's going to restore it because he finds the bad actors. The yellow ones and red ones are bad points in the piece. So why would I go in here and ditch them all because I drilled a hole one place with a Makita power drill and found a little decay and said, geez, it's all got to go? Right? And so when it was just that bad. So that's the story. We find all these guys here. And I know. The whalers have all gone to sea. My cat people can't spell a worth a darn. This is W-A-L-E. The whalers have all gone to sea. But anyway, you see it, the reds and the yellows, and we fix it where it's bad, and here it is here. Fixing it where it's bad. Cost of restoration, $12,000. Cost to replace it, $135,000 in 4 weeks. You just don't do it that way anymore. So the renovation of timber structures is being based on environmental benefits, for example, longevity, load rating considerations, heritage considerations, carbon trading, cost benefits of using advanced methods. The environmental methods are even going further because they're smaller worksite footprints. If I'm out at the tower and I'm going to restore that tower with advanced techniques, I don't want to cut a tree down anywhere around it. If I'm out there at that tower and my plan is to take it down, I got to find somebody really brave to cut each leg and then watch it fall. And I'm going to break trees down, and how am I going to get it out? And if I'm not going to do that and I'm going to disassemble it orderly, guess what happens to the cost? High. And so smaller worksite footprints are pretty important. Less immediate impact on vegetation. Don't break all the trees down and leave a bald spot. Simpler site management, easier to look after. No erosion from works, no beaching. When it rains, you haven't brushed up the mineral soil, so it all washes out. So these are the reasons that we see it in bridges. You see this issue all the time. No cement dust and silica. Silica is the number 6 toxic chemical now in the world. It just moved up to silica. If you cut concrete with a saw, you have to have a urine test once a week now. It's number 6, silica felling. In many countries, you can't build a concrete bridge over a reservoir finger. So for example, if you have a reservoir for drinking water, you can't build a concrete bridge over that reservoir. So there's lots of impacts to these types of things that are meaning timber is coming back. Longevity. We say timber doesn't last. That's the mantra. Timber doesn't last. But I tell my students, I say, wait now, we've said timber doesn't last, but the average age of a bridge in America is 82 years. What's the average age of a concrete bridge? 42. So timber doesn't last. We say timber doesn't last, but timber is the biggest sequestered carbon block in the world today in our homes in North America. Is the biggest sequestered carbon block in the world is our homes, because they're all stick built. So you see, really, it's about not knowing, isn't it? When you don't know, you don't know. And that's the simple of that. So we have this diffuser opportunity to extend life. We have monitor control checkpoints to check them regularly at the ground where what we call hot zones, and that allows us to extend life. Heritage considerations. We used to be in the old days, we could take that bridge out. Can't do it anymore. So now what they do is they put a fence across each end and build a new one upstream where they buy new reserve and watch it fall into the river. And that's being stopped now because governments have realized that that's what managers do. And so now they're being forced to deal with these heritage structures around the world. And this is the big one for me. 22 times less energy to build a timber structure than a steel structure. 22 times less energy. 16 times less than our reinforced concrete. And timber is so great because what? The trees are renewable and they pull CO2 out of the air. It's our roots, see? Timber's in our roots. Simple. So that's the way we roll. A fifth the cost typically to retrofit. A fifth the cost. I'm not telling you what this costs yet. It's going to be the end. You got to stay. You'll be really sick of me by the end of it. You see here. So we got a summary. Cost savings at construction. Carbon, environmentally friendly. Ease of construction to fix it. Reduce cost of maintenance downstream. These are the reasons today that we're seeing buildings and bridges be restored and built with timber. You know, what is this material called timber anyway? Let's talk a little bit about that. I mean, historically, why did we use timber? Well, it was readily available. If we come up to a gap across the river, we cut the trees down and build a bridge out of it. If we were settling an area, we cut the trees down, put them through a portable mill, roughed them up, and made a house. My home that I grew up in has been in the Tingley family for 5 generations. It was built in 1820. My dad passed in 96 and he used it for a money pit for all my royalties. that I made for my patents. If everybody's fixed up an old house, they know what I just said. And you know, that house was beautiful. I skinned off the birch bark that was on the outside of it, squared timbers at odd spacings, and it was lath and plaster, you know. It was a great home. And I grew up in it. I thought it was great, and I wanted to fix it. It cost me to do it, but I fixed it. And so timber was the material of use. And you can see here, it was fit for the equipment. And we put up bridges across the country for our iron horses. And this is the northwest part of our country, where Oregon pine, better known as Doug fir, grew. One tree, one train. If you couldn't make money in the northwest cutting timbers that were the width of this room, growing every 20 feet, 300 feet in the air, you were in trouble. And take a look at these old pictures, because these species that were used in each of the parts of the world were usually the species that were local. And so in different countries, different species became used. Look at this one. I mean, can you imagine having a buck saw that's welded together in the middle and being tasked with the job of cutting that tree down? I mean, come on. You'd have to have a break and a few lunches before you got through the tree. You know, look at these ones. I mean, great old pictures of the origins of our country and the materials that went into many a building in this area.
It's a good thing they stopped that.
Amazing, yeah. Well, there's not much of the old growth timber. We're going to talk about that too. Wait, just wait. So this is what Monday morning's like for me. As you can see here, lots of trouble and lots of timbers. Lots of old growth. That was the story of back in the day with lots of our old timbers. One tree on each strain in Eureka, California. Huge trees. You often hear the term today, old growth timber is gone. Of course, what we've got now is preserved for the most part 10% for our heritage. And we say, well, you know, the old good growth is gone. But that's kind of a misnomer, because we often say it's hard to find good material anymore, great timber. And what we're really saying is that the big boxes have kind of changed the way we buy timber. Home Depot and Lowe's put a SKU number on every 2x4 or 2x6. So when you go in Saturday to do your job at the house, you pick through the wood bunk. Do you take the worst or the best? And so they know that, and so they put a SKU on every one, and so they have 2 premium sorts that are on the top of their sort that normally was here. And what does that do with the rest of the sorts? Pushes them down. And that's what really is going on today in the country, is that it's harder to get our conventional buys because the big boxes are taking the top. And so we say it's hard to find good wood, but really what we're saying is that there's a different sort going on. And so wood really grows the way it always has grown. You can see it here. It's got bark and cambium, growth rings. It's growing the same way today it did 250 million years ago. It's got the same breakup for knots, which are branches, and growth rings and rays and all of this structure. It's the same. Nothing's changed. So I'm moving from Jacksonville, Florida, and my son and I hadn't had much time together because I travel and put on a few of these courses. And so we decided to take 2 weeks and drive across the country together. And the plan was we'd drive half a day and see sightseeing the other half. So one of the places I always wanted to go was to the Petrified Forest in Arizona. Who's been? Oh, you losers. Half people have been there. And so, you know, I'm really interested in this place because it's all these Doug fir trees, bolts laying on the ground. The ashes come over them, pressed them, they've mineralized, and they're there laying on the ground. And if you take them apart and segment them and look under a microscope, you're going to find out something very interesting, that those Doug fir trees grew 250 million years ago the same way they grow today. See, trees don't grow any different. They're growing the same as they grew 250 million years ago. Well, what's my point? Well, my point is that we don't really know, we don't really have the right to say there's no good wood anymore. It's just that it's changed the way we supply wood. Wood has the same properties it had 50 years ago or 90 years ago when this tower was built. It has a radial direction, a tangential direction, and a longitudinal. We put 2x6s in our houses and put them up and down, and they don't shrink much longitudinally. But if you lay them on their side, like the granary, they shrink a bunch. And so understanding that, like log homes, is pretty important. Tangential and radial shrinkage is significant. And it's got cellular structure with open spaces, lumens and cell walls. And wood is held together by lignin. That's the glue that holds it all together. And it needs to have straight grain. You can see the straight grain here between the parent and this plate and the high strength fiber. It's very straight. And here's Doug fir trees. They're geotropic. They grow in response to gravity. Softwood trees grow in response to gravity. They grow straight up and down. That's why on a side hill, they'll grow straight up and down. Hardwood trees are phototropic. They grow in response to light. That's why they reach around. That's why hardwood has more slope of grain problems than softwood trees. There's a difference in how they grow. And you can see this straight grain piece here. And this is what? Well, it's two piles. And in the southern hemisphere, this microfibril angle, when a tree grows, it twists like this as it grows up. The less it twists, the better the grade of wood's going to come out of it. When it dries, it wants to retrace that twist. Well, in the southern hemisphere, that twist is from right to left. And in the northern hemisphere, that twist is from the left to the right. See, nature never gets it wrong. Never gets it wrong. And so here's this guy. This is a pile driven in a railway bridge, and you can see the angle of the grain. And when the train is stopping and starting, he puts a torque on that, and it fails tension perpendicular to grain. Wood is anisotropic. It's different properties in different directions. And it's a good thing it is, because its strength tension perpendicular to the grain is very low, thus we can split it with an axe. We can take two inclined planes, swing it over our head, turn kinetic energy into tension perpendicular to grain energy, and split a piece of wood. Because its weakest plane is tension perp. And so that tells you right there. So understanding this is important. It sucks up water. Who's ever heard of spontaneous combustion? Straw is a cellulose fiber. You put it in the burn, the old days wet, what happened? Boom. Why? Because the cellulose, when it takes up water, gives off heat. When it loses water, it needs heat put into it to dry and evaporate the water. So when it gets partially dry, when it takes up water, it gives off heat. And so a wood piece that's in that tower is the same. It has bound water, that's water in the cell walls, and water in the center. Well, why am I talking about this? Sounds like senseless trivia. That's what my wife says about me. She says I'm senseless trivia. Well, why I'm talking about it is because the average moisture content in a bridge or an outdoor structure in this country is 13 to 14% or 16%. Wood does not decay until it hits 22%. Why is decay 82% of all timber structure degradation? It's the connectors. It's where it's connected. And one of the great things about the tower is all of the guy wires that are there are fastened to the piles with hoops that go around the column. When I looked at that in the picture, I said right away, gee, what a blessing that is. Because oftentimes they go straight through the column and the water goes in that and gets in the middle. And these have hoops. Another reason the tower is still in great condition today. You see, there's a reason for everything. And if you understand those reasons, you'll be better at your job. And so this is what goes on with fiber saturation point. I put this in here. You can see how wood shrinks and expands. Shrinks more tangentially this way than it does radially. And so when it dries at the end grain travel of moisture is 100 times faster than side, and so it makes these patterns. And anybody that's looked at the end of a piece of timber sees that, and that's why it happens. And now you know, because this shrinkage is twice that shrinkage. That's why it looks like that. And so that's what a tree looks like. If you call that a shear crack or a structural failure, you're just simply wrong. It's already accounted for in the standards. It's not a structural crack. It's just nature responding to change in moisture. There's a maple tree outside my home where I grew up, and my dad's dad swung on a swing that's on a big branch of the maple tree. It's still there. And my daughter Beth swung on that swing. Now, how could it be that dad's dad swung on a swing, and that tree's now 100 years older, and my daughter can swing on the same swing? You see, tree is not a grass. It's a tree. Palm trees are not trees. They're a grass. And so trees grow volumetrically, radially. They grow in diameter. They grow with their branches volumetrically. So thus I can put a swing on a branch and it be at the same height 100 years later. So understanding that, why, well, Dan, what's the senseless trivia about that? Well, the senseless trivia is is that when I have 4 columns that are butt down on concrete and they're standing with their tip in the air, it's kind of nice to know that those columns will shrink and expand this way, not this way. So when I see reports say that they've shrunk, I say, well, wait now, they don't shrink this way. And so when I see reports that says it's got dry rot, how many people have heard that before? It's dry rot. Have you ever heard that before? No such thing as dry rot. It does not exist. Google it when you get home. Everybody believes Google, right? Dry rot does not exist. Dry and rot is an oxymoron. You can't be dry and rot. What they're saying when they say dry rot, it's the fraise, better known as S-H-I-T in a polite world. It's what's left over when decay's had its way. It's called fraise, and they're getting into that, and they're calling it dry rot. No such thing as dry rot. And so right out of the gate, when I see reports that say I got dry rot problems, I'm saying, well, they don't know wood. That's how I know. So these vertical cells run parallel to grain. They're longer, and they're very narrow, and water goes up in trees by capillary action. Water will go up in those columns from the concrete. Don't put them on the concrete. Put a meltoid barrier in there, or fortunately, as they are, they're shimmed to point them in. Where they touch on the concrete, they get trouble. The center column in the tower is what? Not on concrete. You put a space in there so they don't suck the moisture. And so capillary action is pretty important. People often say, well, what does that mean, Dan? Well, I say, well, you got the president's tree in California that's 450 feet high. That's 45 stories. Have you ever thought about how the nutrients and sap get from the roots to the tip of that tree, 450 feet tall? Contrary to public opinion, it's not elves. They're not pumping up the water. I know you've heard that story at bedtime. Your dad's told you. No, it ain't true. The real story is capillary action. And when the buds come out in the spring, it creates a draw, a dryness, and capillary action pulls the water all the way up that trunk 450 feet. Just because we cut it down, cut it in sections, and build the tower out of it, does not change it. It still has capillary action. It still does it. Don't put it on the concrete. Concrete will saturate it. So it's hygroscopic. It breathes in and out moisture. It equibulates with its surroundings, and it will equibulate at a number that won't decay. Why does it decay? It's called dew point decay. We put steel with it. Every day the temperature changes, the steel condensates, and it saturates the wood around it, and it decays. It's called dew point decay. And so we watch that all the time. And wood has different densities. I work with wood in different parts of the world that when you bore into it, the chips fall out, and if they hit the water, they sink. They actually sink in the water. The wood's density is higher than water. If you drop a branch of the wood in its water, it sinks. Cape Town ironbark is the densest wood in the world. It's 1.2. It's 20% denser than water. Does not float. And so this species that we have here in the columns is called Western red cedar. It's 0.33. It's 1/3 the density of water. It's very low density. Not as known for its strength. What's it known for? Longevity. They could have had white pine from local, but they chose Western red cedar. Why? Because white pine hasn't got near the longevity that Western red cedar has. So why, if the builders and designers of that tower who knew enough to choose the right species, why would we go in and disregard their great design strategies and cut the sucker down? Are they going to be hating me or what? I'm telling you, that's the way it goes in the world. Just knowing is important. Softwood and hardwood, you can see the permeability, and Western red cedar has great durability characteristics. Strength is affected by knots, splits, checks, and one of the great things about round logs, and this is round, those columns are round. If they were square, are you with me on this one? You ready for it? If they were square, they'd be less strength. Because I keep them round, it keeps the grain right, and there's no slope of grain, and they're stronger. Another benefit to the tower. Weird, isn't it? But weird, but true. So you see, it was affected by knot splits and checks. Up there in that tower, one of the things that I heard was those checks were shear cracks. And there are no such thing as shear crack in a column. Those are checks. It's UV weathering. It's just getting old like I am. And it just needs a little help from here and there. And when you give it, it goes and goes the distance. Moisture affects wood. You know, if it sucks in moisture, it swells. If it gives it off, it shrinks below its fiber saturation point. That's the point at which the cell wall has been saturated. And when we test it, we can find that the straighter the grain, the stronger the piece, as you can see here. This is plastic shift, and it's in compression. You can see here, this is compression perpendicular to grain as it sinks in here. This is bending around log. As I said to you, stronger, it's got no slope of grain because it follows the axes. When I see them calculating the capacities of these columns, and they're using the small end diameter, again, it shows me they have not got any training with timber because we don't use a small end diameter. We use a diameter a third from the small end. How would they know any better if they're never taught? It's not their fault. And so this is not a shear crack. It's a shrinkage crack because we have little bits of wood holding. You often see these cracks. That is a shear crack because there's no bits of wood holding. This one is a shear crack because it's got wood fiber puffed up because the vertical spikes that killed it are fluffing out that wood fiber that's been drifted up like that and runs down the side. Is that a shear crack? No, it is not. That's just shrinkage because there's a boxed in heart in there. There's a pith in the middle. It's close in here, and tangential shrinkage is more than radial, and it responds at a ray line, and that's nature's fault line, and it pulls apart there with cumulative shrinkage. That is a non-structural defect. They're in the column. They're not structural defects. And you can see here, bango, look at it. This is a picture from the tower. Non-structural defects. Look. Look. You see this one? Non-structural defect. So timber can be quite durable. It's important to have its durability. It can handle lots of short-term loads. It has no impact factor for bridges because it has a great short-term impact factor capability. In America, we have the International Building Code. We have AASHTO, which interprets this building code in terms of bridges. We have the National Design Standard for Timber, NDS, and our wood preservation standards. These standards are what engineers use to design things like the tower. The timber industry has a variety of grading agencies because if an engineer designs something, a contractor's got to go buy the timber he designed, and how would he know what the engineer wanted? The engineer puts a grade and a species on his design plans. And then these grading agencies are set up to train people to grade timber, to put grade stamps on them so that users can know what the engineers wanted and they come together and understand it. Here's our dilemma with old buildings. No grade stamps. So engineers don't know what the grade was, let alone the species. And so that's where we come in. We provide a coat hanger, helping them understand this part of it. A lot of people don't know that a heavy dimension timber has an upside down. Does anybody in the room know that a heavy dimension timber has an upside down? They do. If I have an 8 by 12 or an 8 by 16, well, gee whiz, there's an upside down. The big knots go up in the compression top, and the small ones go on the bottom. And so a contractor's got a 50% chance of getting it right. Canadian National Railway built the bridge across Lake Pontchartrain, 19 kilometers. And they bought all new girders, millions of dollars. Within 3 years, half of them are broke. They blame timber. I blame them. Not timber's fault. When you put them in upside down, that's not timber's fault. So understanding how to build with timber is pretty important because what happens when you have a knot and it gets to be big and instead of being up on the top side, it's at the bottom side, it fails prematurely. And it does things we don't like. Because the knot causes slope of grain. Knots are denser than the rest of the wood. It's the slope of grain around them that gives the trouble. Like this. That's where they fail. So watching the knots, keeping them upstairs is pretty important. Now what causes 82% of all degradation of wood? fungal growth. Here's what it needs to occur. A temperature between 5 and 35, moisture over 22, oxygen over 21, and of course wood, the food source. If you have all three of those, wood decays. So if you've got a deck and you bought CCA treated green deck and loaded it up with deck screws from the top, and the water follows the deck screw down and gets at the bright wood in the middle that's not treated, it decays. Thus, our treated decks last 10 years or 15 years in this country and they're gone. Worse than that, the deck plank itself might stay, but the joist underneath where you put the deck screw into is gone because it holds the water, doesn't have a chance to breathe and away it goes. Can anybody relate to that? And so that's why it fails. And so here's how fungal colonies go away. You have a spore, they're floating around in the air here. You can't see them, they're on that piece of wood. You can go to Home Depot and buy a clean piece of wood. People say, I'm going to go buy a clean piece of wood, it's got no spores. They're wrong. You can't see them. That timber, the minute it has the right ingredients, temperature, moisture, right, and oxygen, it's going to decay. And so you can see it here. The spore grows a hyphae. It grows a foot. It secretes an enzyme. That enzyme is acidic. After it gets a little big and forms a colony, it puts a hyphae out, forms a flower, and you'll see flowers on the side of decaying trees. And what do? We put a caustic, anhydrized salt, a dewatered salt in here, and it neutralizes that pH wave and suspends the decay causing fungi. Great idea, eh? The best things in the world are the simplest. That's what my wife says about me. So you can see here two types of rot, brown rot and white rot. You can see. Brown rot, what is that? That's the rot that basically eats the cellulose, leaves the lignin, the glue. The white rot, what's it do? Eat the lignin and leave the cellulose. There's only two types of rot in the world, about 6,800 of each, 7,000. And this stuff is nature's cleanup crew. People say, well, it's too bad. I say, well, it's not too bad because it's a good thing there are fungal colonies because guess what? If there was no fungal colonies, you couldn't walk through the wood because every tree that ever fell over would still be sitting there. That's the cycle of life. We just don't want the cycle of life in our towers. And so we want to suspend it in our towers and not have it go the distance so that it doesn't end up looking like this. That's what we don't want, isn't it? So don't paint them. We shouldn't have painted the tower. Okay, so you see the leaning stairways here, and they think that's all about the stairways. Well, they didn't put any bases underneath these, and they sunk down into the water, and that's what's caused all that. And they've got oak stair treads, white oak stair treads, which is really goat. We make barrels out of white oak. Why? Because it's got tyloses. I was on a cruise down the Danube with my wife not long ago, and we went into a winery and went downstairs in the cellar, and the guy's talking about all his wine barrels made out of oak. And I put my hand up and said, what type of oak in it? Is it red or white? And he said red. And I said to my wife, she said, he's lying, let's go. Because you don't make oak or whiskey barrels or wine barrels out of red oak. You make it out of white oak because white oak has tyloses in the lumen and it keeps the liquid in the barrel. And that's the same thing that keeps it from decaying. And so the choice of the stairwell treads was the best choice you could make. It was white oak. So when I hear people say the stair treads were sucking, and I'm thinking, wait now, it's white oak. Why are they sucking? Well, wait now, maybe those outside columns are sinking down the ground because you didn't put a what? A base underneath them. So here it is. This is white oak under a microscope. Tyloses, these little bubbles in here. Nature's way of making it more durable. The hyphae can't grow through here. It's a viscoelastic bubble. Here comes the hyphae growing across grain. That's filaments of it. Why is it growing across grain? It's white rot. It grows across grain, and it's a little bit harder to stop. You can see it right here. White oak stair treads. And here's what it looks like under a scanning electron microscope that we take. That's tyloses. You see, when you get into the nuts of something, you can start to understand why it happens. That's what we're going to discover some days, the cure to cancer. Who's lost a loved one to cancer? Aren't we waiting for it? And it's going to be so easy because they're going to figure it out one day. It's going to be like my block. It's going to fall glue side down. It's like toast when it falls on the floor. What's it do? Butter side down or butter side up? Guarantee it's butter side down. That's what happened to me, and it led to one of my biggest patent successes. That's what's going to happen with cancer, and that's what happens here with knowing what's going on. What's that? A fruiting body. You see it on trees. That's a hyphae grows out. When the colony matures, grows a fruiting body. And you can see the hyphae right here under microscope. This is oak, and you see a little flower out here. There's another one here. You see a little flower out here. Here's a colony, right here. Here's a fruiting body. Another fruiting body. Fruiting bodies. You see them all over. Fruiting body out in the tree. You've seen those out there? Those are fungal fruiting bodies. And here's what happens when you let a fungus go. 80% loss in compression perp. It got what? Decay in the center behind the treatment because they vertically spiked it down through here. The water got in the middle, decayed out from the inside out. It lost compression perp to grain and blew out the cribbing. Cause and effect. Cause and effect. There I am standing looking at it because now they've got a 2-inch drop in the highway right here because of cause and effect. It's not wood's fault, guys. And here we are in America with what we call our hydroclines. This shows you, I come from right here, Jacksonville. 100 days out of every year wood decays in Jacksonville because the temperature's right. Up in here, a little different, right? This is what's called a decay hazard map in the United States. You can see where we're at. Another reason why this tower should be going the distance. It's dew point decay that drives this tower. And because we have these conditions right for decay, and so people say, well, how do you stop it? Take one away, just take one away. So I'm on a skidoo, I'm going across the northern part of Manitoba on the snow. I see a stick coming out of the ice. I stop, this guy stops, he sees the stick, he digs around it, the stick gets bigger. He marks it with GPS and goes back and they keep digging. They use X-ray and in there, locked in the ice, is the HMS investigator. They uncover it and all the skeletons are still in the bed, underneath blankets, everybody's dead. Every piece of wood in that boat is intact and the same as it was the day it got locked in the ice. We did what? We put the bridge in the fridge. And so that's it. That temperature was missing. What happened here in the Black Sea? Oxygen was missing. It was waterlogged. What's this guy doing in the bayou? He's down with the alligators. Why? Because he knows that log's a lot of money. Southern yellow pine. It sunk down. There was what? No what? Oxygen. Or this guy here. I took my daughter to King Tut exhibit, and this was in his tomb, and all these artifacts were timber. They were 3,000 years old. None of them were decayed. What was missing? Moisture. Wood doesn't have a use-by date. It's knowing how to use it. If I'm going to put a drain on top of that crossbearer, it's going to decay right here. And then I'm going to send the crew around to fix it. Instead of putting a $2.49 extension, I'm going to say water and wood are great. I'm going to let the water keep going. Then I'm going to take 2 pieces of iron bark, cant wood, treated. And because I can't get them in next to this guy, I have them shallower, so I packer it up with a shim, bolt it to it, and then all of a sudden it shrinks because of seasoning. I have to go back, put another one in. Then by that time, the decay is coming over in this guy. Nary a time did they put an extension on it. See, it's not wood's fault. It's not wood's fault. They had to keep it off the galvanized pipe, but they let it go on the wood. You know, put a little gap in here so the water gets off. When you put no gap, what happens to your kickboard? It decays. Don't paint it. Stain it. And put a little angle. Don't put vertical fasteners in here. It'll save it. Don't paint it. This is 4 years old. Wonder why it goes away? Don't paint it. Don't paint it. Don't let the vegetation get around it and hold moisture and allow that moisture to create decay. And don't put vertical fasteners in it. When you put vertical fasteners in things, it lets water into the middle. 1892, what part of that fastener is still good? The horizontal part. The vertical is gone. Look at the old square head cast nuts. So it's this, look at that. The vertical's killing it. There's his hand stuck in it. The vertical's killing it. And this is a map you can get right off of Google, yet engineers don't use it. They still drive stuff from the top, and you can get that right off Google, showing you decay-prone areas. Horizontal, every one of those bolts, that assembly goes 3 times further. Look at this one. Drift pins into the middle behind treatment. It's gone. Drift pins into the treatment, bright wood behind treatment. It's gone. Look at these. Ruined every one of them at 20 years. Put mastic around it, still didn't stop it. The water went down and ruined it. Ruined it. And put a brand new bridge together, oh, still vertical fastening. Nothing fixes stupid. And you can see it. They still keep doing it, right? Now here goes this. We got great ideas, right? Because look what we're doing. Worth fixing. This is hazard class selection guide for different woods. Get the best wood for the worst conditions. And what did they do? Chose cedar. They didn't just get those columns for free. They chose them. They got $500 to do it, and they chose the best. Why would we go take them out now? So you can see here, these are the top 10 things. Anybody wants this, get my business card after. I'll send this to you for free. Those are the top 10 things you can do when you're building with wood in your own house, in your own area, in your own building. Do these top 10 things, and your buildings go 3 times further. Right here. So I want to play you this one because this is a story about what happens when you don't do things right. And this is what I'm going to play right now. I'm a real covered bridge fan. And a place I grew up, New Brunswick, has 54 of them, one of the highest concentrations of covered bridges. And people think they made a cover on the bridge so that Clint Eastwood could film the bridges of Madison County. Well, no, that isn't true. And they think it's because they want to be able to have a place to get their horse out of the rain. No, that's not true. There's all kinds of kissing. You know, they're going to have the kissing bridges. No, that's not true. Why we put covers on bridges is to keep the water off the joints so they lasted longer. And so when you don't know how to manage them, you don't keep the water away from the ends, and moisture gets into the very ends where they attach to the foundations. And watch this for me if you think timber bridges are not built strong. This is a 186-foot clear span covered bridge, and you can see it sailing down the river. 2 hours it's in the river, like Noah's Ark.
The Cherryville covered bridge, built in 1927, carried away by the floodwaters of the Canaan River.
Look at the length of it. It's 2.5 times longer than your tower is tall. It's floating down the river intact and never breaks up.
But also a loss with immediate consequences. The people who are now cut off. 2 hours later, as the sun sets, the old bridge gets caught under a new bridge, caught and held in place against the abutment by the fast-moving current.
So they paid a contractor $250,000 to fish it out of the river. He turned around and sold the wood out of it to make 6 high-end chalets. He sold the wood for $500,000. He got $750,000. Because why? There was one bad actor in the whole bridge that let go, and the whole bridge sailed down the river. When I was choosing slides for this presentation, I thought this was particularly relevant. Why would we toss a whole tower away because of one bad actor? And that's relevant. So you can see here, right, this is a covered bridge. When they start screwing around with it in a marine environment, putting untreated steel, it goes sour. They have to put this bridge. And when they did that, they got that and voted out. Because that was the one thing people could come together on. They might not have agreed on much about politics, but they knew something. That when we forget the past, we lose track of the future. And so that's what it's about for us. How do we find these defects? We have these interior techniques for finding bad actors, guys like this. You got to find them before they find you. We can do it with a resistance drill like this one. Gives you a local understanding of what the decay is at that very point. It gives you an output, and that's one of the techniques we use. We can use moisture meters like we did on your tower to find out what the moisture is. And then we go in and do core samples, assay sample testing, which we take to the lab and test and understand its species, its moisture content, and its decay, and what type of decay it has. These assay samples then help us cross-reference our non-destructive testing techniques to allow us to be able to better understand the structure, as you can see here. We bag them, we look after them, and we take care to understand exactly what the structure is. So this bore sounding, which is what we've done in the past with the tower, drill holes in it, gives us local information, no indication about the quality of the material, and no indication about the depth of the bore and its quality. We drill holes in things like this. We drill holes in things. Destructive testing, and this is what happened when we drill them. We get this result because we drilled it on one side, thought it was good enough, and the annulus thickness on the other side was this big, and this pile happened, and that happened. We'll do it 1, 2, 3. 1, 2, 3. See, when you don't know, bad things happen. So compression wave testing is important. It helps us understand the strength and stiffness of something by putting a compression wave through it. We won't read these because I'm pushing. You can see here the blue box just like that one. You can get them for $6,800. Calibrating them is another $17,000. They're about $25,000 a piece. And Stephen's using that because he's looking around that vertical fastener and figuring out where the decay is. And this guy here, when they hit it with a stress wave hammer, it fell out. And we have a chart that we use that helps us calibrate them, and there's a lot of science to it. We won't get into it tonight. And then we core to cross-reference the numbers, and then we can do things like this. Use a triangulation. It's called electronic pulse highlight and outline diagnostic. It's called ephod. I kind of thought it was fitting because in the Old Testament it talks about David putting on the ephod and understanding which way the Lord wanted him to go. Well, you can see the same thing here as you look at this cross. It's finding the bad actors, as you can see here. So here's John cross-referencing it with this and finding the reds and yellows. Because we don't want this to happen. And if we use advanced technologies, here's what happens. 56 fewer false positive, 26% fewer false negatives, so that these things don't happen. Find the bad actors before they find you, like this. It's too late once it's fallen out of the bridge. That's what Dave's doing there, seeing what the time is, 34:74. Watch how you do it. Don't get across the shrinkage crack. Do the right types of measurements like the boys did out at the tower. Find these bad actors. And away you go, getting the reds and yellows. Reds. This guy here, look, sapwood gone, and here's the little hole where the bore sounded it. We walnut shell blasted it after to find where the bad actors were. Look, that's decay. Finds the soft tissues. It's not concentric. If you think you can find it by hitting it with a hammer, go for it. You know, you can see in here, look, you got to use technology to find it. Look at that one. How would you find that? Oh, wow. Nature's not concentric. You know, one arm's a little longer than the other. So it's just the way it is. So deterioration by other agents here, mechanical damage. We can have degradation due to rust, metallic, that is what we call ferric degradation. We can have impact damage like this. We can have rusting pieces. They don't rust the wood, they just embrittle the lignin. It pulls away from the fastener, and you've got plenty of that in the tower. And you can see it here, rusting, untreated steel. Because we have embedded and exposed corrosion zones in the country, as you can see here. And we watch these as engineers, because our people want things to last a long time. This is one of the apostles in Australia. We want our bridges to go a long time. This is in northern India. It's nearly 675 years old. They grew it. And they liked it so much, they grew a double-decker. These are real stories. These are real pictures. They're not Photoshop. And they grew their handrails. And why did the bridges last so long? They grew their connectors. And so if we build our connectors right, they'll help our bridges go the distance. People say, well, concrete lasts longer. And I say, well, you're wrong. And we can see these problems here all over the place with concrete. In Toronto right now, it's the largest infrastructure disaster in North America, $1.8 billion fixing concrete bridges with an average age of 32 years. So I heard this story in the previous reports about building a steel and concrete tower to replace the pot tower. And I thought to myself, well, they don't know about steel or concrete. They wouldn't be saying that. That's rust-resistant steel. It's 28 years old. I guess it didn't go either. So all materials have their Achilles heel, but here's wood still in service looking like this. Wood's very forgiving. It does a great job of going the distance. How old is this bridge? It's in Japan. 576 years old. It's called the Leaf Spring Bridge. Why would we think that our structures can't last? If they're properly inspected and maintained, they don't have a use-by date. They go the distance. I just came from here was it yesterday? Yesterday. Out Mount Rushmore. They had me go in and look at these two iconic bridges as you just go into Mount Rushmore. North Dakota owns both of them. They're iconic. They're 56 years old. The engineers went to them and told them that these bridges had a use-by date of 40 years, recommended they spend $23 million to replace them. They're iconic. They had me come in to look at them. I could only find 3 bad actors in both bridges, and the cost of restoration was $300,000. And I was prepared to recertify them for another 100 years, and they laughed at me. They said, 100 years? They're already 56 years old. I said, well, that's great, because it's easy for me to offer a 100-year guarantee. I'm 65. and laughed. They didn't laugh. Nobody laughed. You can see underneath beautiful timber bridges. Beautiful, you know. Beautiful timber bridges, you know. Like George Burns used to say, I don't even buy green bananas. You know, I don't know how long I'm going to go, right? You can see, here's it, look. So, you know, reds and yellows. So extending our old timber structures is the way forward. How can it be that people say timber doesn't last when we've got structures around 100 years old and nothing in steel and concrete that old? You know, we got this going on in concrete. How is it that timber doesn't last? I'm going to put them on again because I thought it'd be good to show them twice. Timber tower restoration. This is Gymnast State Tower that I talked about earlier. It's a favorite of mine because you get worn out walking to the top. It's 48 to 49 meters. It's about 174 feet. Clear span, clear height, no guy wires, 3 columns, gray iron bark, spliced together in spots, built by hand a long time ago with a fire tower at the top. And they searched me out because they knew I liked to do stuff like this, and I said, I'll take it in a heartbeat. Let's go find the bad actors and fix that tower. And you can see here the stairs. Same sorts of things. Bottom of the columns, flaring out because they put them right on the concrete. It's bulging out against the stirrups, you can see here. Bulging out. Gray, the red zones at the bottom. You can see the reds. Get up in here, you got some places where there's fasteners, you get dew point decay. Bottom flare out. Find those reds and yellows you can see in here. See the flare out? Even though they're butt down, they're still flaring out. You see this decay pocket underneath the landing. No wonder it's shut down, eh? Look. There's just a few areas like that. The same here goes. Look, they've been drilling, trying to find out what's going on, you know, figuring it out. Look how the tower's torquing. These are cross braces. This is looking sideways. And this 3 tower, it moves almost 2 feet side to side when the wind blows. At the top. If you're up 175 feet and clear 3 and it's moving 2 feet, you feel really uncertain. And you can see the brace twisting out. And so these are the stair treads going to the top. You can see them worn here. They painted them. You know, looks good. Paint hides a multitude of sins. In our business, we call it structural paint. You can see here. Up the stairs it goes. Look at the top. So we rappelled down it to inspect it. We put our rope access guys on it and went all the way down it, inspecting it. And basically found out where the bad actors were and how we would restore it for this top. And what was afoot there? They wanted to take this off with some huge crane deal or helicopter, cut it off at the top, put that down and make a display out of it and charge people $5 to see the old fire tower. And then they were going to lay it down on its side and take it away. And the cost of doing that? $1 million. Cost of restoring it? $1 million. Do the math. So you can see here all the way up the top. These are interesting splices that it had in it. Here's where we restore it. You can see the guy's rope here as he's hanging down by doing the testing. These shows you the stress wave times. Now we drew a picture. Look at this picture. There's the only places that were red. Find the bad actors. Find the bad actors. Look, just a little yellow. Yellow means it cannot carry a known live weight, only it's dead. Red means it can't carry its own dead weight at a particular point. And these are the reds and yellows in it. And this is the design. We developed this design. It goes out to tender this next month to restore this tower right here. That's right now. And we're going to put some guy wires on this particular tower to make it cheaper to fix. This tower, what would I do with this tower? I hear saying, geez, if he hadn't got here, I was quitting. He said, so here comes this tower. Look, 1929, 1931, built, $500. Can you imagine building that tower for $500 today? Money was hard to come by in those days, and the tower represented a great way forward for the people in a community as it provided a way to look out over the beauty of the land beyond all obstacles. If you were going through the Great Depression, to be able to get up a tower and look a distance would have been a great blessing. Because your problems would have been crowding you pretty bad, wouldn't they? And so to be free to see and to dream, much the same way as the people of the day gain strength. Engineers don't like to read this stuff. I know they don't, but I like to put it in there. I'm a sucker for timber. So people gain strength to face the day, face the future, seeing how things would go beyond the days of the Great Depression. The community in the United States persevered through world wars, economic booms, busts, through all the country grew. During all this time, the tower also persevered. Through that whole time, the tower persevered. No maintenance, poor maintenance, you name it, it persevered. It stood the test of time. When the steel and concrete towers they were talking about replacing it with, they were talking about lasting longer, were falling down and being taken down. This timber tower was going the distance. Do the math, go do the facts like I have, and find out just what I'm saying is absolute truth. The absolute truth. It stood the test of time. When the experts said that timber towers don't last, only steel and concrete ones do, the timber Potawatomi tower stood and still stands today. That's the simple facts of it. So I went in and condition state rated it according to this table. I said if it's 1, it's good, it'll go 80 years. All the way down to 5, it's a 1%, less than 2 years it would go. It would be unsafe. This is a rating table. You can get this again from me if you want to after, just see me. That's how it's rated, the standard rating table from around the world today for outdoor structures. The 5 main this is the results in a synopsis paragraph. 1 simple paragraph. 5 main tower columns were tested, and 2 of the corner columns were found to be in poor condition, with the bottom 4 feet of the columns in heavily degraded state, causing an overall condition state rating of 4. The center column is in good condition with a condition state rating of 2. The 2 other corner columns have a CSR of 3. The CSR of 4 for the 2 corner columns southeast and southwest is predominantly governed by isolated areas in the columns that can easily be restored in situ. These 2 columns and the short length of the heavily decayed wood on the bottom of both columns is the primary reason that structure is rated for 4. It's a 3-tiered structure standing approximately 75 feet. The tower is closed to public right now, as I found out today. The structure is comprised of 4 wood columns that were not randomly picked. They were not sawn. They were round. They were cedar. They knew what they were doing. It was chosen for a reason. They had collars that went around them, not through them. They did it for a reason. They chose white oak treads for a reason. The tower just didn't happen by accident. It was there for a reason. That's why it's here today. And underneath each of the column corners, there's shims to make it point inward. The one in the center is lifted up to let it breathe. The stairs wrap around the central wood column to provide access to 3 observation levels. The first at 25, then 50, and then 75. The top observation level is open with handrails and used as a viewing platform. The tower is located in the top of Government Bluff, limestone quarry. It provides excellent views of the state park in the state of Wisconsin. So we look at it here, you'll see photographs of stairs and handrails in here. You can see them by looking through here. Some of them painted. The outside corners on the stair rail kind of settling. You can see some of these guys getting decay. You can see the verticals in here. These sorts of fix-ups in any tower are called minor maintenance. It's called minor maintenance. As you can see in here, here's the collars instead of going through them with the guy wires. You can see that painted it, wouldn't have done it. What if I had my way, I'd walnut shell blast it or acrylic bead blast it and then stain it with a stain less than 28% solids, Cetol 1 and then Cetol 2-3, and that wood would brighten up and you guys would have to put sunglasses on when you're around it. It would be beautiful. As you can see here, you look at that and you say, that guy's had it. There's some UV weathering there. It's kind of lost some section around the knots. It's got some shrinkage cracks around it. It kind of looks old. And the first thing you think of is toast. When we do the internal non-destructive testing, it isn't toast. And so you can see there are places that are toast. And you can see those. My little girl could pick that one out. I don't have to be a rocket scientist to figure that one. And so you can see here these places. But these decks and rails and systems it can be easily restored. It's not a big bill. And we can take that plywood down. And you can see here the big 4 columns going. Look at that, guys. Now you know why I went through the first of it, didn't you? But you're thinking, this guy sucks. He put me through all these damn slides. What's he up to? I want to go home and feed the cat. You're like, come on, what's wrong here? Jeez, you know? Look, this is it. Now you know. When you looked at the previous ones, all the reds and yellows, there's no reds and yellows. That's what I'm saying. But look at that. I mean, these, and come on, man. Yeah, there's a bad guy right here, but he's isolated. You know, you can get him. Look, there's some at the corner, look, here, but very few yellows. Yeah, you can fix, look. They put tar on it. I don't know if some of you guys are responsible for that. I'd never done it. And I'd get it out, let the wood breathe. Don't coat it, don't tar it, let it breathe. So I say to my wife all the time about me, when I'm home on Saturday, I want to work out in the shop. I say, let me breathe. She'll come out and she'll, I got this big list for you, you know. I haven't seen you for a week. I want to do this, this, and that. I said, honey, come on, I got to be able to breathe here for a minute. That's what this wood does. It needs to be able to breathe. Look, a few reds. These guys here, you're looking at them and seeing this and you're knowing why it's got, look. Northeast tower. You know, that's it. Look at that one. The center tower leg has no decay in it. The one they singled out.
Cut it out.
None. There's no decay in it. Why is it shut down? It's got a few weak links, right? It's that analogy I told you, right? You're hanging from the steel bridge. Don't take the average, you got to take the least. But go fix that steel link and then hang from it. See here, that's what it's done when you put it graphically and we drew it out. You can see right off where the bad ones are, right? Go fix them. So analysis of cores revealed specific gravity. That's the ratio of density of wood to density of water. It was Western red cedar, highly durable, as you can see here. There, in these southeast columns, they got some voids in there, which we found. And as you can see, this tower can go the distance to be able to be restored. This is the cores the guys took from it. So we know what we're doing. We identified them under microscope and followed the proper keys to identify the species and its grade and put together an in-kind repair strategy like this for the element. This is an advanced fiber. We gave a couple of options. And here is the design. Hot off the press today. I was over there working at the B&B. Putting this into the PowerPoint an hour before tonight. So nothing like just-in-time strategy. You can see this is the specifications page. This is the replacement requirements page here. You can see this is the drawing showing the posting detail here. We'll take care of this guy here with a typical posting detail where the reds are. How do we do that? We support the tower with guy wires. We then turn around and cut it, put in another one. There's a specific design characteristic. You see that space in there underneath it? And we'll post that piece. You can see samples here. And this shows you how it's done. We hold that column up. Then we take a section out, put another section of Western red cedar in with a specific design detail here, and put it in action. Now, if you've never had any training in timber design, you probably won't know what to do here. But I've got the odd one done. 1,350 to be exact. So you can see here, this is the cost. You're seeing it for the first time. Not even your buddy Sean has seen this. I can't see it. You can't see it. That's what my wife says all the time. Okay, look, 249,000. You see here.
Yeah.
And this is what? Here, walnut shell blasting. If you want it structurally sound to be able to walk up that stairs, then you're talking 170. If you want to fix the columns to keep it from coming down, it's less than 100,000. Eagle was 750. When you know where the bad actors are, you can fix them at much lower cost. Understanding the situation is part of curing the situation.
So no fibers, none of that.
I just chose one that I thought was holistic for you.
Okay.
I didn't put fibers on it. I figured on using kind for kind, sectioning and diffusing, natural. If you want to see fibers, they'll be a little cheaper. But I figure when you got it this low, you might as well have it the way, right?
Okay.
Yeah. So you can see this is one, same height. So I thought I'd show you one that I inspected, designed, went and fixed. It's the same height. Does that sound good to you? Four-legged stool, still the same. Taking pieces out of it. Let's look at it here. Finding the reds. Look. What did they do with their guy wire or their bracing? Went through it, and it ruined it. You guys have collars around it. And so you can see that guy's bad. Well, we're going to take that guy out. And you can see we put guy wires to hold it for safety. You can see here to keep the tower from coming down. And they had engineers come in and say, let's put concrete around the bottom of it to restore it. And they floated concrete around the bottom. It ruins its kiss of death. They go away 66% faster. So we had to jackhammer the concrete out and then get at the stirrups from the old base. And there's the old one in here with the old stirrups. We connected the new stirrups to the old one, cut out the old one. You can see it here now connected and the concrete cut away from it. You can see these guys. Here's the new pile segment that was changed out for the bottom, put in place here. You can see it here. The concrete floated around, and the engineer of record for the council came around. He said, "Dan," he said, "too bad." He said, "Your pile was too short. I always tell you to measure twice and cut once." And I'm saying, "What? Measure twice and cut once? What are you talking about?" He said, "Well, look, you got an inch too short." I'm the inch too short? I said, "I planned it that way because I want the air underneath it so that the moisture doesn't come from the concrete and ruin it again." Like your what? Center column in your tower. And so here it is here. You can see it fixed up. This is an internal shear pin. It's inside, so you can't see it. This is the outside. That's a rotation spline glued into it. You can see there. And basically, we put that back in service. Do you remember what it looked like? Hold on. Whoop, right there. This is it. Okay, come.
So we still have the bolts going in there?
Yeah, those nasty bolts.
Oh.
I know.
They're still there, huh?
Yeah. They're not rusted either. But anyway, you got that piece back. And there it is. That guy goes away. Look how bad he is. I mean, most engineers look at this and condemn the whole tower. Because they don't want to face it. They don't know how to face it. They just want to get rid of the tower. Hey, what? Wood doesn't last, right? Isn't that what you've heard? Doesn't last. So it's easy to tell a client wood doesn't last when you're showing them that. Because he just believes you right away. It's a lot harder to fix it like that. Yeah, or dry rot, exactly. And you can see what he did here. This is the next one. I already told them that the other two columns that are buried in concrete are going to be up next because they've been ruined, you know. So we put diffusers in to try and extend them, but down in here, it's not going to work. And so you see here, we don't have the guy wires going through. They're horizontal lagged in and sealed, and this is a hook here to carry the new guy wire, cross brace rather. New timbers inserted into it. And these guys here, you see them all over. They put Meltoid on the top. Get rid of those guys and don't paint it. Get rid of the paint. So we got rid of those. Let it put copper naphthenate, 2% reactive agent, heavy saturation 3 times, then anchor seal, which is paraffin wax and water, and get rid of that metal. Because every day at temperature change, that metal sweats. And fix these guys where they're at in situ and put this thing back in service. The maintenance items listed above can be completed at significant cost savings. That's what I talk about here with the tower now, back to your tower. In addition to the cost savings, using advanced timber restoration techniques, repair of the structure has been followed to give benefit. Reduce site disturbance, reduce potential for erosion, preserves the landmark for the community, extends the life of existing assets, and utilizes these assets more effectively. Finally, it's highly recommended that all structural elements be diffused, extend the life, diffuse them. Exposed bright wood should be treated with copper naphthenate to seal it, end grain, and anchor seal. In summary, it's easier saying it's good he's done. In summary, Potawatomi Tower has stood the test of time for nearly 90 years. It is weathered and contains conventional UV section loss as well as non-structural cracks and splits in some of the elements. The tower has 2 columns with advanced decay and cavities in the bottom 4 feet. However, well over 90% of the critical structural elements are capable of continuing on in service to the community and with the help of remedial treatments that can be implemented as the tower stands. It has served the community for decades and deserves the opportunity to continue to do so. The cost of remedial work is a fraction of the cost of replacement. The cost of tearing it down and disposing of the tower will be the same magnitude as repairing the worst of the heavily degraded zones. The best option working forward is to restore the tower and extend its life utilizing advanced strategies. Clearly, advanced non-destructive testing and assay sampling testing by an IAS-certified test laboratory has shown that the vast majority of the primary structural elements are in a condition suitable for continued service. Proper maintenance will extend the life. The implementation of proper repairs will bring the structure back to proper occupancy capacity. With these actions, the Potawatomi Tower can go on to serve the community for another 90 years. There I am. Thank you. Rewind.